All right, buckle up because today we're diving headfirst into Einstein's universe. We're talking black holes, but not just as cosmic vacuum cleaners. We're talking about them as potential bridges to other universes.
Where space and time twist and bend, maybe even tear.
Okay, so let's break this down. We're using this Veritasium video as our guide. Something strange happens when you follow Einstein's math, and they start with this scenario. Imagine watching your nemesis in a rocket heading straight for a black hole.
Okay, first of all, Nemesis. Where do you come up with this stuff?
You know me. I could have a little fun with it. But picture this. As your nemesis gets closer to the black hole, you'd think they'd speed up, right? Gravity and all.
Newton's law. But Einstein saw things a bit differently.
And that's where things get really wild. They wouldn't speed up. It'd look like they were slowing down the rocket. And even weirder, time itself would slow down for them. Imagine being frozen in time, right there on the edge of oblivion. That's the event horizon, the point of no return. Not even light can escape that.
And see, this is where we see that big difference between Newton's and Einstein's ideas about gravity. Newton knew something was off about gravity, the way it acts instantly across huge distances. That's strange, but he couldn't explain it.
Then Einstein comes along with this completely revolutionary idea. What if gravity isn't a force at all? What if it's all about how mass and energy warp space-time?
Think of a bowling ball on a trampoline. It creates a dip, a curve. That's kind of what massive objects do to space-time. Earth isn't being pulled towards the sun. It's more like it's following the curves the sun creates in space-time.
Right, it's like it's stuck in a cosmic rut. So how do we even begin to visualize something that complex?
Einstein gave us the tools, his famous field equations. Now, I'm not going to pretend I can just scribble those down. Those are notoriously complex.
Definitely above my pay grade.
But the important thing is what they represent. These equations describe how mass, how energy warp space-time. And the first person to really crack the code to find an exact solution was Carl Schwarzschild.
And this is where it gets interesting. This was back in 1915, right? But he wasn't in a lab. He was on the front lines of World War I.
Now that's dedication. Calculating artillery trajectories by day, unlocking the secrets of the universe by night. And his solution, what we call the Schwarzschild solution, it describes the space-time curvature around a single, stationary, non-rotating mass, a simplified model of a star, or, a black hole.
Which is where those space-time diagrams come in. I've seen those with the cones, right? To show the past and future. But near a big object, they get distorted, like pulled toward it.
Exactly. Those diagrams are key to visualizing this. Space and time, they're not rigid. They're more like a fabric that can be stretched, compressed, twisted. That's gravity. And the fascinating thing about Schwarzschild's solution is that it predicts these 2 points where the math kind of just breaks down. Singularities.
Singularities, those are points of infinite density, right? Like what's at the center of a black hole?
You got it. One's at the center of the mass, yeah. But the Schwarzschild solution, it predicts another one a specific distance away from the center. That distance, that's the Schwarzschild radius, or as we usually call it, the event horizon.
So that event horizon, the edge of a black hole, it's not just some random line. It's where gravity is so strong that space-time is like infinitely curved. Nothing can escape, not even light.
Hence the name, black holes. But here's the thing, the whole black hole idea, it was so out there that even Einstein, he wasn't sure about them at first.
Wait, really? The guy who revolutionized gravity thought black holes were a bridge too far.
Hard to believe, right? Back then, a star collapsing into a single point of infinite density, way too radical. And this was decades before we had any real proof of black holes.
So how'd we go from no way to, okay, they're real?
It was a slow process. New models, new ways to even picture these warped space-times.
Like those projections we talked about. Different ways to look at them.
Exactly. Imagine trying to draw a map, but up, down, all directions are constantly changing. That's what it's like. We needed new tools to understand this crazy geometry. And then came the observations. Quasars, those super bright, distant objects. Active galactic nuclei, shooting out jets of energy. And then finally, actually seeing stars orbiting something that could only be a supermassive black hole.
So it all just kind of added up. From math problem to, oh yeah, those are out there.
Pretty much. And the more we learn about them, the weirder it gets. Remember how we said the Schwarzschild solution describes a non-rotating mass? Yeah, well, real black holes, they spin.
Hold on, spinning black holes, does that create like a cosmic tornado or something?
Kinda. It drags space-time along with it. Think of a whirlpool. Roy Kerr, he's the one who figured out the math for a rotating black hole. Even more mind-bending, let me tell you.
Okay, I'm hooked. Lay it on me. What's so different about a spinning black hole?
Well, instead of just an event horizon, You've got layers now. There's the ergosphere. It's this zone outside the event horizon where space-time is being pulled along by the black hole's spin. Like imagine trying to stand still on a spinning carousel. You just can't. You're forced to move with it. That's the ergosphere.
Whoa. So even before you hit the point of no return, you're stuck in this crazy cosmic whirlpool.
Yep. And then, of course, you still have the event horizon, the boundary, no escape. But things get really interesting when we think about what might be inside a spinning black hole, not just around it.
Wait, inside? I thought that was it. Game over. You get stretched out like spaghetti by the gravity.
Well, according to Kerr's solution, that singularity at the center, it's not a point, it's a ring. And some physicists, they think if you somehow survived going past the event horizon, if you could handle the gravity, you might be able to pass through that ring singularity.
Pass through like a portal. Are we talking wormholes now?
We're venturing into wormhole territory, yeah. Those theoretical tunnels connecting different points in space-time or even different universes. It's wild, but mathematically, it's not impossible.
I thought wormholes were just sci-fi stuff. You're saying Einstein's equations actually allow for them?
They do, but there are a couple of catches. One, the type predicted by these solutions, they're super unstable. Gone in a flash. Poof.
So much for shortcuts through the universe.
Not so fast. There might be other ways to make stable wormholes, ones that don't just collapse, but those would require something that's exotic.
Exotic.
Exotic like that.
Exotic matter.
Come again.
Picture a substance with negative mass. It would push gravity away instead of pulling it in. It's theoretical, but if it exists, it would completely change how we understand physics.
So we're talking about like phantom particles that behave in ways we can't even imagine, all to maybe hold open a theoretical tunnel through space-time.
Sounds pretty wild, right? But remember, black holes were once considered sci-fi too. Good point. Okay, so you're saying maybe, just maybe, stable wormholes could exist, but we need a lot of ifs. We need exotic matter, we need to figure out how to use it, and then there's the whole surviving a black hole thing.
Yeah, minor details. But the fact that we're even talking about this, that it's part of scientific discussion, shows how far we've come. Who knows, maybe one day we'll look back on these ideas like we do now when someone mentions a flat Earth.
So we've gone from black holes to spinning black holes, we've dipped our toes in wormholes and exotic matter. Where do we go from here?
Well, there's one more mind-bending concept we haven't explored yet. White holes.
White holes. The opposite of black holes.
Kind of, yeah. Nothing can escape a black hole, right? With a white hole, nothing can enter. Like a cosmic fountain, always spewing stuff out.
So black holes are cosmic vacuums, and white holes are like cosmic leaf blowers.
Exactly. And while we haven't actually observed anything that's definitely a white hole, they come up in Einstein's equations.
You're kidding. The same equations that predict black holes also suggest these opposite things exist. This is getting weirder by the minute.
The universe is full of surprises. But white holes aren't just weird fountains. They're also connected to time.
Time. Now you've really got my attention. How are white holes connected to time?
Think about the event horizon of a black hole. Point of no return. For a white hole, it's a point of no entry. Nothing crosses from the outside in. But something could come out, something from elsewhere.
Elsewhere, like other universes again?
Could be. Some think white holes are the other side of black holes, connected by wormholes. Bridges through space and time. Imagine that singularity at the center of a black hole. What if it's not the end, but a door to somewhere else?
Okay, now you're messing with me. A door to another universe. That's next level stuff.
It sounds crazy, I know. But remember, we're talking about things that go beyond what we usually experience. My point is, the math allows for it. And the universe loves to surprise us.
Yeah.
Look at what we've learned about black holes just in the past few decades.
That's true. I guess when you're talking about all this, anything seems possible. But if white holes are out there, where are they? Why haven't we seen any?
That's the million-dollar question. Some theories say they're super unstable, even more than black holes. They might pop into existence and then vanish almost instantly.
So trying to find a white hole would be like, what, catching a soap bubble in a hurricane?
Pretty much. Or maybe our instruments just aren't good enough to see them yet. Or maybe they're hidden in plain sight. We just don't know what to look for.
It's wild to think these cosmic fountains could be out there, maybe even connected to other universes, and we might be totally clueless.
That just shows how much there's still to learn, so much to explore and discover. That's what makes studying the universe so exciting.
I'll say, so we've gone from like the bottom of black holes to these hypothetical white hole fountains. We even talk about wormholes and exotic matter. This has been wild.
And through it all, we're following Einstein's ideas.
Right.
His theories that changed how we see space, time, gravity, everything.
It's crazy how one person's ideas can have such a huge impact. I mean, we're talking about stuff that used to be pure sci-fi.
It really shows you the power of curiosity, that drive to explore what we don't know. Einstein opened up this whole box of cosmic mysteries, and we're still trying to figure it all out.
And the thing is, we've barely scratched the surface, right? Every answer just leads to more questions.
Exactly. And those questions are even more mind-blowing than the ones we started with.
Yeah.
That's what makes it so fascinating.
Makes you think about those first physicists who studied black holes. They had equations, their imagination, and that's it. A lot of people probably thought they were nuts, but they kept going, pushing the boundaries, and look what they started.
Think about Schwarzschild figuring this stuff out during World War I. Can you imagine that feeling? Realizing you've glimpsed something that big, that fundamental about how gravity works. It gives me chills.
Me too. And it makes you wonder, what else is out there that we think is impossible? What's the next big discovery that'll turn everything upside down?
Maybe it'll be actually observing a white hole, or finding exotic matter, or who knows, maybe something we haven't even thought of yet.
That's what's so cool about science, isn't it? It's all about exploring, always pushing into the unknown.
And we get to be a part of it. Every new observation, every new theory, it brings us closer to understanding the biggest mysteries of the universe.
So as we wrap up this deep dive, let's hold on to that sense of wonder, that drive to learn, to question, to stay curious. Because who knows what amazing things are waiting for us out there, just beyond what we can see right now. Until next time, keep looking up and keep asking those big questions.
Yeah.
The universe is full of surprises for those brave enough to look for them.